Welcome! In this video, we present our mechanism topology optimization method. This is an innovative method that allows us to design vehicle suspension mechanisms in a creative way. The animation you see now shows how a new mechanism of a vehicle's rear suspension can be computationally synthesized by our novel method. We will present an overview of our new method and its application to designing suspension mechanism for electric vehicles under a tight space constraint. When we design vehicle suspension mechanisms, we must consider various design requirements such as mechanical performance, layout constraints, and manufacturing cost. Especially in electric vehicles, there is an increasing demand to accommodate large battery packs and motor assemblies for longer driving. However, it is very difficult to design suspension mechanisms with satisfactory kinematics because the space for a suspension is extremely limited. To overcome these suspension design challenges, our team has come up with a revolutionary autonomous design method and succeeded in finding unprecedented suspension mechanisms by using the method. Our novel suspension design method is based on what we call as the mechanism topology optimization method, which was first established by our team in 2014. To give you some idea of our method, let us consider the design of two-dimensional linkage mechanisms that generate the desired output motions at their end effectors. Even without baseline design, our method should be able to find the desired linkage mechanism topology and link dimensions. The animation shows the way how our method generates the desired linkage mechanisms using an optimization-based iterative algorithm. As the iterations go, some lines become thicker and the others disappear. After some post-processing, we can finally identify the desired mechanisms. Now we show an animation illustrating the iterative procedure of our mechanism topology optimization. Our model allows us to find a space-constrained rear suspension mechanism of vehicles, especially suitable for electric vehicles. Let us move on to the figures. When we used a regular design domain, we obtained a conventional multi-link type of suspension as shown in Figure A. In contrast, when we used a smaller design domain, we found a new suspension mechanism as shown in Figure B. In this section, we compare the two suspensions, the conventional suspension and our new suspension. Here, we call the newly designed suspension articulated X-shaped link suspension, in short, AX-link suspension. We use the screw axis theory to show that the AX-link module of our new suspension behaves as equally as the link parts with spherical joints in the conventional suspension in terms of kinematics. Well, we won't go into the detailed kinematic analysis of the new AX-link suspension. But as you can see in the figures, our new suspension exhibits nearly the same kinematic behavior as the conventional one, even when our suspension occupies much smaller space. This is how electric vehicles can benefit from our new method. This project was funded by the National Research Foundation of Korea and by Hyundai Motor Company. For your reference, we listed our recent work on our mechanism topology optimization method. We hope you enjoyed our video. Thank you for your attention.